Alright, so the purpose of this video is to go over the Centripetal Acceleration Lab and the instructions for you coming in. So hopefully you can start the lab immediately upon coming into class, because all of you are totally watching this video ahead of time and not having to get your fellow students caught up because they didn't do it. That would not happen. Alright, so the purpose of this lab is to prove this equation. Now, proving any equation in this requires that knowledge of chapter 1 of what shape should the graph make if this equation is in fact correct. But unfortunately, it's really hard to measure acceleration independently, and it's really hard to kind of measure all of it. We kind of need to get all of them. So here's what we're going to use. We've talked about this setup a little bit in class already. Okay. We're going to have something like a pen casing, or in this particular case, a marker casing. Okay, you're going to have a string in between them, and tied on one end will be a large mass, and the other end will be a small mass. Okay, you are going to swing this around, and we're going to make measurements based on this situation right here. Now, I know we've already gone over this in class, so this next part will be done relatively quickly, but I do want to make sure it's on there. This is also on the lab itself. So if I've got my kind of pen casing here with a larger mass right down there and a mass swinging from this, I'm going to label this guy as mass hanging and this guy as mass spinning. And we're going to make a couple of assumptions right here. Anytime I mention assumptions during a lab, you should write them down, because basically I'm telling you what you should talk about on your error analysis, because we know our numbers will not be perfect based on the fact that these things actually exist, but we're going to try to keep them as small as possible. The first assumption that we're going to make is that friction does not do anything in this situation, which of course is not true, which will change some of the results as well. The second one that we're going to do is we're going to assume that the spinning mass is perfectly horizontal. This is also not true, because in actuality, the force of gravity of the spinning mass causes there to have to be tension in the Y. The reason that this is relatively accurate is we're going to try to do our best to keep mass spinning relatively small. Now, the problem that you'll find in just a minute is that we actually also want to make spinning mass, for different reasons, relatively larger. So there's going to be a balance of that, because you're going to have to decide spinning mass in your class. But we're going to try to keep it small enough that force of gravity doesn't much matter. And if that's the case, we can kind of approximate that this is roughly horizontal, which of course it isn't actually, but we'll deal with that here in just a second. If I do a force diagram on both of these, let's see if you can see this. Okay, I think so. I maybe need to draw a little bit bigger here. For the mass hanging, if I spin it around so it doesn't move, then we should get force gravity of hanging, and tension should pull it up. And we should know that those two are in fact equal to each other, because this is not accelerating. If I do a force diagram up here, since I assume it's horizontal, we should just have tension. Now, if I sum the forces on each of these, we find something interesting. Summing the forces on the bottom, specifically in the Y, the mass times acceleration, like I said a minute ago, not accelerating. So there we go. Sum of forces in the Y, we should have positive tension, minus force of gravity hanging is equal to 0, or tension should equal to force gravity hanging, which is equal to mass of hanging times G. Okay? Then I sum the forces up here. Sum the forces in the X is equal to mass times acceleration in the X. And the only force acting on it should be tension. And it should all be in the X. Because of the assumption we made earlier, it shouldn't actually all be in the X, but pretty darn close. Now, we equal mass. This, which mass is this? This should be the spinning mass, because this is the inertia of it, where it's accelerating. It's mass spinning. And this acceleration right here, we can see in my example, okay, that the, let's get this out of the way here, that the tension should stay 90 degrees to the velocity, and therefore should create a centripetal force, which is not a new force, it's just when force is perpendicular, and therefore should create centripetal acceleration. So since sum of forces is perpendicular to velocity, we can say acceleration centripetal is vt squared over r. I don't know if that's very easy to see either. I hope so. All right, now, we know that tension is equal to this right here, and tension is equal to this right here. These are, in fact, the exact same tensions, which you can, of course, see by just taking a piece of string and pulling, right? If I pull this hand this way, it's the exact same amount as this hand being pulled in that particular direction. Since they are equal to each other, we get mass hanging times gravity is equal to tension, which is equal to that tension, which is equal to mass spinning times vt squared over r. This complicated looking equation, again, I want to reiterate that it's just this. This guy is actually the net force being created. This is actually the inertia, and this is the actual amount of acceleration. It will become important later. But our purpose was to prove this equation right here. So what we're going to do is we are going to specifically look at, so I'm going to make a small change to that equation because I think it's a little bit easier to measure this other way. Yeah, let's make that change first. Okay. I told you that AC is equal to vt squared over r. We have also learned that it's equal to angular velocity squared times r. And there are going to be some measurements in this that are easier if we use that equation instead. So let's go ahead and get rid of this guy and instead use omega squared times r. All right. So what we will do in a lab is what we do in every lab. We make measurements of one variable. Okay, we change one variable. We measure what happens to the other variable, and everything else should be kept constant. Change colors here. Okay. So the relationship that we are going to look at here is we are going to look at angular velocity versus mass hanging. Or in other words, this is going to be your y, and this is going to be your x. So I'm going to take my fancy ridiculous equation right here, and I'm going to solve for y. So mass spinning and radius, I'm going to divide them underneath. So I have mass hanging times gravity divided by mass spinning times radius, okay, is equal to omega squared. So I will square root both sides, and that will equal omega. Now my y variable is to the first power, so I can look at what the mass hanging is doing. That right here is to the square root. So based on this, the shape of my graph, if this equation is correct, should look like a square root function, with omega being on the y and mass hanging being on the x. Let's look at what the constants should be. Well, this is all underneath the square root. And technically, I should be able to pull this out. Square root of mass hanging times square root of this mass. So this right here, that's multiplied next to my independent square root of my independent. That should be my k value. And nothing is added next to it, and therefore my b value should be 0. So k is equal to the square root of g over mass spinning times radius, and b value equals 0. So like I said, we are going to change these values, and then we're going to keep everything else the same. So the first thing to understand about this lab that kind of makes it complicated is you guys are going to be doing a large lab together, okay? To make any of these sets of data, probably the best case scenario, even over the course of 2 days, is that just one group might get 5 or 6 points of data. This is not going to represent, probably, we're not going to see any shapes like this because there's a lot of error built into this lab, which is going to make it pretty darn complicated to do. So we are all going to work together. Now, how can I make sure that all of our data belongs together? The first thing that you have to do is decide constants right here that are all the same as each other, okay? Now, I'm going to tell you one that we're all going to use that I have found to be advantageous in the past, but the first thing that your entire class is going to do is each independent group is going to try to figure out what mass spinning works the best so that you can get really good results. Okay, so you'll go out, we will use rubber stoppers. You can measure their mass. You can change their mass in basic ways, just like, staple some tape on there, or staple some paper to increase the mass, so that you should all have this guy right here that's spinning is the exact same mass. Now, here are things to look out for. Okay, number one, we already addressed that mass spinning better be relatively small because this negates how much force gravity it has. So you might say, why don't we just keep it really, really small? The other thing mass spinning does in this problem, though, that you have to be careful of is right here. It provides inertia. So the smaller that your mass spinning is, the larger your acceleration. Or in other words, if you put something super tiny on there, you got to spin crazy, 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 crazy fast, all right, in order to get it to stay where you want it. So there is going to be a balance of this. Okay, I gave you an example of class telling you that this guy is 6 grams, so that at least gets you started in the conversation. But I would say for at least the first 10-15 minutes is you guys want to make one of these and practice and see what mass up there makes sense. Take time in the beginning to get this good, and all of the rest of your results will go a lot faster. If you just rush into taking measurements, that's going to make this a lot harder. Now, let's talk about what measurements you're going to take. Okay, one, obviously after you've got the mass spinning, that's a constant. This will not change for everybody. They should all have the same mass. Number two, I'm going to tell you for radius, 25 centimeters works great. So how do you set that? What you'll do is you'll get out a meter stick, make a measurement of 25 centimeters on here, and then just grab one of my markers and mark it down. Okay, then when you go out to actually use it, your mom's probably gonna have to practice a little bit, like hold this in place, get it going, but you can't keep holding it because you're changing the force. So you need to try to find exactly what speed matches with keeping that radius at exactly the same spot. So you measure the mass, you set the radius. Okay, now we should also measure mass hanging. This is what's going to change. What's down here is what we are actually changing. Meaning, if I increase the mass down here, technically what I do is I increase tension. Increasing tension up here means I increase acceleration. And of course, increasing acceleration, we expect to have an inverse effect on the angular. Oh, sorry, no, it should also increase the angular speed as well, the more the more acceleration that we have. Okay? Excuse me. So you need to be in communication with one another, and we'll put together a document where everybody can see everybody else's data at the same time. But you need to be getting different mass hangings down there. If you all do the same mass, it should just be a dot, which is not going to give us a good data. This needs to be well spread out. We need to use small masses and large masses and everywhere in between in order to get good data. The last thing to cover on this is how do we measure angular velocity? Well, angular velocity by definition is one circle divided by the period, or how much angle is covered in a certain amount of time. Well, let's talk about an issue here. Okay, I could just do one loop. The problem is, if you've seen our example in class, one loop on this is probably around 0.2 to 0.3 seconds. And if you'll remember, you have a human reaction time of 0.15 seconds all over the place. So we just use a stopwatch. That's not going to be very accurate. So here's what we have to do. Number one, we have to go through more loops. Okay, we just do. We can't just go through one loop. We'll decide together. We'll do, again, this is nothing that you decide as a group. We're going to do 10, 15, 20. The more loops you do, the more accurate the measurement will be, but obviously the longer it'll take, and so more annoying to get that measurement. So you guys kind of decide as a group, do we do this 10 times? 1, 2, 3, 4, 5, 6, 7, 8. Okay, or do we do it 15 or 20, or what makes the most sense to balance being accurate versus not? taking forever to get this particular measurement. Okay. The last thing that you can actually do to make this pretty accurate, although once again this will also slow down and it's up to you whether or not you do, is you can use the slow motion camera on your phone. Take a slow motion video of this spinning around. I would still do multiple loops. Okay. Excuse me. Still do multiple loops. But then you can time that, and then when you're done timing it, you can divide by 8. Because slow motion cameras slow it down on your phone by a factor of 8, which will make it vastly more accurate as well. But obviously, if you get out your camera and have to do all this process, it's going to take longer to do it. So that's up to you. What's kind of more important? Is it more data, which is going to take place because we can do this relatively quickly, or more accurate data? Conversation for you guys to have. Okay. When you do multiple loops, the way that you'll calculate angular velocity is simply going to be the angle of one loop, 2 pi, multiplied by n, where n is the number of loops you went through. In other words, it's 6.28 radiuses in one circle. So if I go through 10 circles, 6.28 times 10 means there's 62.8 radiuses in in 10 circles. Time, you'll notice on the bottom, is no longer capital T because that's just one circle. It's not all of them. And you don't need to do anything to time because obviously time is going to get bigger by about 10 times if you take 10 revolutions. So it should be 2 pi times number of revolutions divided by time gets you this. We will have a Google Doc that you put all of this information into, and you should be able to see your information as well as other people's. We'll talk more in detail about what that looks like when you get into class. But hopefully right now you understand the following things. 1, the purpose of the lab is to prove that equation. Through this work, what we saw here, sum of forces, is that equation is true if this messy equation is true. We chose to look at the relationship of angular velocity versus mass hanging, which means, by solving for omega, we should get a square root function with the constants of k is the square root of g over mass spinning times radius, and the b value better be 0. And the last thing that we discussed is how to make all of those measurements. Radius is going to be 25 centimeters or 0.25 meters. We decided that. Mass spinning is going to be up to you to decide. Okay. Mass hanging should just be measuring with the triplet beam balance. And angular velocity is the conversation we just had. It's going to be 2 pi times however many loops. Yet again, something that you guys as a class are going to decide how many there's going to be. That should be it for the lab. If you have questions, which undoubtedly you do, go ahead and ask me at the beginning of class, and we should be able to get going. Thanks.